Okay, I'm Richard Valenzano, and this is joint work with Shahab Jabari at the University of Alberta, Jordan Thayer at SIP, Ronnie Stern at Harvard, and Nathan Sturtevant at the University of Denver. I'd also like to thank the ICA for providing some funding for the company. So what I'm going to be talking about is this bound suboptimal business that Lila talked about yesterday, where we want provable bounds on solution quality. But now we're going to talk about beyond epsilon admissibility. We're going to try and generalize to other possible cases that you may have. So we're going to look at how you would create algorithms for basically any type of solution quality requirement that you may have. And we're going to develop algorithms for doing so. We're going to look at three particular frameworks of algorithms in which you can go from epsilon admissible to other things. And I'll get to what that means in a second. And then I'm going to finish off with showing that we can actually create these algorithms for particular kinds of bounds. So I'm going to look at a relatively new kind of bound called additive bounds, which I'll explain in a moment. So I'm going to just start with a little discussion about suboptimality measures and suboptimality bounds. Here's just a graph. The black nodes are goals, and there's a number of solutions here where the start is at the top. You have this one in the middle with cost 4. That's the optimal solution. There's one on the left with cost 6. A little more, not quite as good, but not too bad. Here's this one here that has cost 13. Now we're getting farther away from our optimal solution, and the final one with cost 10. And the question is, which of these are acceptable for your particular system? You're creating a planning system. You want it to define which ones you're going to be happy with, essentially. If I'm doing an optimal planning system, only that one in the middle is acceptable. The rest are they're just not good enough. That's essentially what you're saying when you're saying you're doing optimal planning. When you're doing status slicing planning, sure, you'd like the best solution, but you're accepting that that's probably not too easy to do, so your first task is actually just find any solution. Finding a better solution is sort of the secondary task, but that first task is just give me one of the solutions out there. So any of these are acceptable in some sense. The final case is bounded suboptimal planning, which kind of splits the difference. Now you're defining that there's a set of solutions, not all of them perhaps, which are acceptable. So for example, perhaps you're saying that last one's just not good enough, whereas the other ones are. Epsilon admissibility has been the traditional way to do this. Bounded cost is much more recent, and maybe we'll discuss that a little bit later, but epsilon admissible is the one that's the most popular. And essentially what we're saying is if you have an optimal solution, we'll say the optimal solution cost is C star, an algorithm is said to be epsilon admissible if any solution it returns is guaranteed to have a cost that is no more than a factor larger than the optimal group. That factor is given by 1 plus epsilon. As the system designer, you assign what epsilon is, and you get to decide what the acceptable solutions are in that way. And there have been many algorithms in the search literature that are epsilon admissible, things like weighted A star, optimistic search, A star epsilon, EDS, and many, many others. So this is what it kind of looks like. Here I just have a graph where the x-axis is the actual optimal solution cost to your problem, and the y-axis is what you're going to allow for what's the maximal acceptable solution cost for that corresponding solution cost. So for example, if we're talking about optimal search, if we have an optimal solution cost of 10, well then you're only allowed to return solutions that have cost 10. Likewise, if it's 14, you're only allowed to return ones with size cost 14. So you have to return a solution in some sense in this blue area, although in reality you're just talking about that line. Epsilon admissibility now says, okay, we're going to increase the region in which you're allowed to return a solution. So if I have epsilon at 0.2, I'm allowing 20% suboptimality, so we're talking about that red region. Whereas an epsilon of 1.5 allows even more space. Epsilon admissibility in some sense is putting a limit on the ratio, well, that's exactly what it's doing, it's putting a limit on the ratio of C over C star, and that limit is 1 plus epsilon. So you can think of this as you have this suboptimality measure, which is just given by the ratio of these two elements. So you're putting a limit on this ratio exactly. So in this case, again, if we just look at it, if we just calculate the suboptimality of our various solutions, this one is acceptable because its ratio is 1.5, whereas this one is not because its ratio is 2.5. But is epsilon admissibility, is that ratio the only way to measure suboptimality? What about something like just the difference between the two solutions, the difference between the two costs? Or another question is epsilon admissibility the only way you can define the solution quality requirement? What about something like this? Here I'm asking that any solution that you return has got to be no larger than optimal plus the log of optimal. So it's almost, in some sense, it's a tighter bound, because as the solution optimal solution grows, you're requiring something closer to optimal than epsilon admissibility level, which grows linearly. So here, for example, is an additive bound. Here we're saying the solution has to be no larger than optimal plus a constant, not multiplied by a constant, but plus a constant here that you define. So here the red region is much different than the one before. Now we're not growing with optimal solution cost. You're always requiring the same difference. And this suboptimality, this additive bound corresponds to this type of suboptimality where you're taking, calculating it as the difference between your optimal solution cost and your actual solution cost. Here's sort of the other way where you're allowing even more space as you grow, as your optimal cost grows. So we're talking here about return a solution that is no larger than the optimal 2 some power alpha. And here I have what alpha 1.5 looks like. And this corresponds to this strange looking suboptimality measure. And perhaps this is not your suboptimality measure that you would prefer, but it is perhaps one that someone else may prefer. So what we're really looking at is trying to introduce more flexibility in choice. We want to understand what existing algorithms can be extended to do. What else can they be pushed to satisfy? What other things can they do? And what they can't do. And the reason for this is to provide additional flexibility for a system designer. So if I want to create my planning system, maybe I have my own way that I like to define suboptimality requirements, or maybe I have my own way that I'd like to measure suboptimality. And now we'd like to give you options, algorithms that will more correspond with your designs in some respects. The way we're going to do that is we're going to define suboptimality in terms of a function. So we're going to define this bounding function, which is just a function from the positive reals to the positive reals. And we're going to say that an algorithm satisfies a given bounding function if any solution it finds is going to have a cost c such that you're returning a solution that is no larger than b of c star. So what this looks like, for example, if I'm talking about optimal search, is the optimal bounding function is just the identity function, because I'm requiring that c be no larger than b of c star, which in this case is in fact c star. Epsilon admissibility looks like this. This is the epsilon admissible bounding function. 1 plus epsilon times x, because it corresponds exactly to the epsilon admissible criteria. Here's what the additive one would look like. Now we're talking about the additive, the bounding function in this case is b of x is equal to x plus gamma. And here's, say, what that earlier one would look like, the logarithmic one, where we're allowing solution suboptimality to increase with the optimal solution cost, but it's got to grow slowly, unlike, say, epsilon admissibility, which grows linearly. So the task now is, you give me a bounding function, let's give you an algorithm to actually satisfy it, so that we can satisfy any particular requirement that you have. One thing you could do is you could use an optimal algorithm, but this is kind of a degenerate case. Sure, if you return an optimal solution, that's going to satisfy any other possible suboptimality requirement, but it completely defeats the purpose of even allowing for suboptimality in the first place. When you're saying I'm going to allow suboptimality, it's usually because you're expecting that finding an optimal solution is just too difficult or it's going to take too long. So by me saying, well, here's an optimal solution, I'm not really doing anything for you. So we need another strategy which will hopefully trade off this fact that you're allowing for additional suboptimality in exchange for perhaps a faster search or a less resource-intensive search. So we're going to get to that now, is how we're going to build these algorithms. So I just want to point out that epsilon admissible algorithms cannot be used directly. So for example, if I have this type of solution quality requirement and I want to use WA star, it's not at all clear how I would set W unless your optimal solution is already known. If it's not, then I don't know exactly what weight here would correspond to that sort of solution quality requirement. But we can modify existing epsilon admissible algorithms if we do so appropriately in order to satisfy a large class of bounding functions. We do this, in fact, in the paper in 3 different frameworks with best first search, iterative deepening, and focal list-based search, which are things like A star, epsilon, and ES. That's the name I use for them. In this talk, I'm only going to talk about best first search. If you want, you can ask about the other ones later or see the paper on how we do that as well. So when I mean best first search, all I mean is A star and other algorithms of that kind, which have some sort of evaluation function and iteratively select nodes based on that evaluation function. So A star just uses F, where that's G plus H. BFS is just going to use an arbitrary evaluation function phi. And it's going to iteratively select the one on the open list that has the lowest value according to phi. So if we're talking about a graph like this, phi is going to determine which is the best node at each moment, just as A star does. And I'm going to use this notation here, BFS phi, to indicate I'm talking about a best first search that is using evaluation phi at that particular moment. So for example, A star is BFS BFSF, where F is just G plus H. And that's the node it would select there. And your evaluation function can use whatever information you would like. So for example, if you're talking about greedy best first search basically says, I'm going to ignore the G cost of nodes. I'm going to focus only on H. And for example, greedy best first search is BFSH. The one thing I will require for these best first search algorithms is that you are reopening nodes on the closed list. So this is unlike perhaps the last talk, for example. So here we have 2 nodes on an open list. I'm using this red circly thing to denote that that's the open list. This node on the left is going to be expanded because we're doing A star here. It's going to find a better path there to this new node this node that was previously on closed, and you're going to have to put it back on open. Now, in order to satisfy a particular B, we're going to need an appropriate evaluation function, because that's really what changes the behavior of an algorithm like best first search. Now, I'm going to use WA star sort of as inspiration, because it's been an algorithm that's been around for a long time, and it's known to work pretty well, not always, but works pretty well generally. And it's something to build on in some sense. So this is the evaluation function that WA star uses. It's G plus 1 plus epsilon times H. And if we look at the epsilon admissible bounding function, which is just 1 plus epsilon times x, we know that, well, we can derive this fact here, that essentially the WA star evaluation function is G plus B of H, where B is the epsilon admissible bounding function. So we're going to use, this sort of suggests that maybe